Hey everyone, my name is Zhilei Xu, a postdoc at MIT. Very glad to give the talk here. The topic of my talk here is the on-sky calibration of CMB experiments. So CMB, since it was discovered in 1965, it was a great discovery for physics and also even for science. So when it was discovered, Penzias and Wilson, they measured the temperature of CMB across the sky. They found that it's isotropic. It's the same temperature all across the sky, which is very odd because at that time when CMB was generated, the universe, the horizon of the universe where causal distance can be connected is about this size, around like 1 degree. However, the entire universe somehow knows to have the same temperature across the sky far beyond the horizon. So this is very odd. And then as the technology advances, we keep pushing further and further down. We did see anisotropy, but it's very small. This is underneath. This is underneath the very it's like 300 microkelvin on top of 3 Kelvin. So it's one part of 10,000 basically. So this is by Planck satellite. So this is actually, it's not entirely isotropic. If we look deep enough, it's anisotropy, and we can see the anisotropy. So with this, we can actually get a lot of information out of the universe by taking the power spectrum. This is taking the power spectrum of the map. So this is like doing Fourier transform, but in space. The x-axis is the multiple. On the left is the small multiple, means large angular scale. On the right axis is the small, is the large multiple, which is small angular scale. So this featureful kind of curves actually encodes some basic information of the universe. Say, what's the components of the universe? 80, about 70% dark energy, 25 dark matter, about 5% of ordinary matter, like that made up you and me. Also, another thing is by measuring this, the peak of this first, the location of the first peak, we measure the universe is flat. It's not curved. It's not a little bit curved. It's not a little bit curved positive, and actually it's just right, be flat. It's very fine-tuned from a physics point of view. And then that's why people came to the theorized that the cosmic inflation kind of paradigm. It describes the universe went through an exponential expansion at the very first, like 10 to the minus 35th seconds. This solves the previous dimension problems. This kind of dramatic expansion actually stretches the horizon at the very early universe to beyond the horizon we thought it was. That's why we see this uniform radiation from the CMB. The second is the flatness problem, because maybe there was some curvature at the early universe, very early universe. It was the expansion that stretched so much, and right now the curvature, we cannot measure it anymore. It's like we measure the curvature of the Earth on a piece of paper. It is curved if you try very hard, but it's beyond measurement. And also another thing is the very cool, very exciting is the CMB anisotropy must have come from somewhere. As a physicist, we want to know where it comes from. It's kind of a fundamental question, because those perturbations eventually turned into large-scale structures we observe today. So this cosmic inflation actually explained that those anisotropies came from quantum fluctuation initially and was blown out to the entire astronomical sizes. So this is a very attractive theory. And then we can actually see signatures of it from CMB polarization. The CMB polarization can be decomposed into E mode and also B mode. One is curve-free, one is curly. You can see as demonstration here. And then only the inflation generates B mode polarization at the largest angular scales. So this is the signature, B mode polarization, basic power spectrum. So now I'm showing these 3 power spectrum. This is provided by Planck collaboration. So these are 3 power spectrum. First one is the temperature power spectrum we just saw. The second one is the E mode polarization power spectrum. You can see with the effort from multiple experiments, we have a kind of roughly good idea of what this looks like. And then at the bottom, very faint, it is the B mode power spectrum. So it's much fainter than even E mode. So that's why we are starting to get a hold of it by increasing sensitivity of the measurements. So this also shows the trend of the CMB field advancement. So I think before WMAP, I think it was like 20 or 30 years ago, we could not even measure this very well, the brightest one. Right now, not only we can measure the temperature power spectrum very well, we can also measure the E mode polarization and even B mode polarization. And in the future, we will push all the way through to the B mode polarization power spectrum. It's not. So what was the driving force that enabled this? It was the instrument development, which I can give another talk about, and also something I want to talk about here today is the calibration method. We keep knowing our instrument better and better to better precision. So the importance of calibration. So before I even started doing CMB measurements, my understanding of it is that you build your instrument and you make your measurements. That's it. It turns out as we finished building our instruments, I realized I was missing one key part, which is we need to know the instruments. We design and build instruments with some like model understanding, but it's not necessarily good enough to reflect the reality. That's why we need to know the instruments and then make some measurements. So after all, this is like all the digital numbers. Raw data from different experiments are nothing but digitalized numbers. You can save them on disk. It doesn't matter whether it's from it's like a $10 billion James Webb telescope or it's from your digital camera, like $100. So they are the same digitalized number. It is the calibration that provides the knowledge of the instrument that we can use to interpret digital numbers to physical meanings. So that's kind of the importance of calibration, a bridge from like from just raw digitalized numbers to physical meanings. So at some point, understanding the instrument is as important as building the instrument, because if we build the instrument and we don't understand it well enough, that sometimes that is the money not very well spent, because we have not exhausted the potential of the instrument by knowing it better, by calibrating it better. So that's the topic of this talk today. So I'll first start with the experiment called Cosmology Large Angular Scale Surveyor. It's short for CLASS. It's in the Chilean. It's in Chile on the plateau that houses several CMB experiments. They're CLASS, Simons Array, ACT, Simons Observatory. This is what CLASS looks like. CLASS observing. We have 2 mounts and 4 telescopes observing from the site. And then let's see, what do we need to calibrate for CMB experiment? First of all, we want to talk about intensity. The first thing first is the system efficiency. This is testing the efficiency of every optical components and the detectors. So we've tested them individually before we integrate and deploy that. But this is the final test, putting everything together, how efficient the system it is. If it's very efficient, it will increase the sensitivity. If it's not, then it's not good news. And then after that, we need the pointing and also beam. Basically, this is testing the alignment of optical components. So it's like a digital camera. If it's not aligned very well, the picture we take, it will be a little bit blurry and also very sharp. This is basically testing that. Because we build the instrument ourselves, everything here we need to check. And then another thing, especially important for CMB experiments, it is the far side lobes. We need to test the suppression of optical systematics, because that's for the CMB very precise measurement. This is very important. We don't want any signal leaking from the far side lobes into our signal. That will confuse us in measurement. So in the instrument design, we implemented several rounds of optical systematics design, but then it is the final on-sky measurement that will give us the answer whether these designs are valid and is sufficient in terms of suppressing optical systematics. So these are 3 things: system efficiency, pointing and beam, and also far side lobes. Let's see how we did it. So first of all, this is talking about the 40 gigahertz instrument. It has a very large beam, 1.5 degrees. So that's why we actually, in a very novel way, we use the moon, which is 0.5 degrees in diameter as the calibrator. because the moon is very bright and also not too bright to saturate our detectors. So actually it gives us a huge dynamic range in calibration. However, the moon is not exactly a point source for us. We built a very comprehensive model, a thermal model of the moon like this. So basically determining, depending on which side of the moon is facing the sun and which part we're observing it, we basically built this lunar thermal model with different tilting angle to basically mimic what we will see on the sky. So and then with this, we immediately calibrated the system efficiency to be like 48%. This is very high, and also we got this number with very high confidence because of the brightness of the moon. So and then we move over to pointing and also beam and pointing. So this picture, I did it in combining these two information together. So each of these red dots is a beam, is a measured beam. It's not from simulations, it's from measurements. You can see some of them looks not as good like this. Some of them looks very good in the center. And then they are all put in the location that they are pointing at exactly. So you can see the 40 gigahertz telescope for class is has a very big footprint. You can see this entire focal plane is about like a 20 degrees wide, 20 degrees tall, and then the moon is only this size. So so this actually reflects the instrument design, which is like this. So this is the focal plane of the instrument. Each one of those things are a feed horn. So each of the beam is actually from one of those feed horns you can see here. And then this pattern, this hexagon pattern, we are seeing here on the sky pointing and also beam actually reflects the fact that everything is aligned, and also each of the feed horn has a sharp beam. So this verified the instrument is aligned and also performing as expected. So this is a pointing and also beam. Last one is the far side lobes. Here it is. So this is the first time in the CMB field, I think, that we presented, because by using the moon, which is so bright, the far side lobes, the beam map all the way to 90 degrees. This is the entire hemisphere. And also in addition, this is to show the far side lobes. So we tuned the color bar here from -30 to -50 with the peak normalized. That's why we see everything is saturated around here and in the center. So we don't see any side lobes all the way to -50 dB. So this is another verification that the far side lobe design is working for us. The design to suppress far side lobes is working. And then this intensity, then we can move over to polarization. Polarization calibration is important because this B mode polarization power spectrum we are going after. So I'm showing this plot again. This is the temperature, E mode polarization, B mode polarization, and with their relative amplitude. You can see if although there are three spectrum, but we see them in the same sky all the time. We observe them at the same time. We need to distinguish them. They all show up in the same sky. So how do we do that? So if we don't do that perfectly, if we have any leakage, say from temperature to polarization, it will easily overwhelm the E mode and not even to say the B mode power spectrum, right? And then in addition, if there is an E mode polarization leaking to B mode, it will also overwhelm the B mode measurement we are going after, which is determined by the detector polarization angle. So here, this is the importance, because to achieve this goal, we need to distinguish them with high confidence. And also polarization calibration is also very hard. It's not, first of all, not many significantly polarized celestial sources are there on the sky. Secondly, the polarized celestial sources are not very well understood. It's to the precision that the CMB experiments wants, they are not very understood. So that's why we came up this new way, also with the moon. Basically, the moon itself is not polarized, but if we look into its detailed structure, if we go to the edge of it, we see the P wave from Fresnel equation, also S wave is the transmission of these two waves are different. So when we go to the edge of the moon, we actually see some net polarization coming out of it in this pattern, in this kind of radial pattern. And then the instrument we have measures Stokes U, which is which is this direction positive, this direction negative, and then it turns out to be a quadrupole we expect from this moon polarization pattern, which is orthogonal to the monopole pattern that we observe for the intensity. So that's a way we can constrain the temperature to polarization leakage. Here it is. We then constrain it to be 10 to the minus fifth, which is orders of magnitude better than the requirement for class. And then one step further, we can use this kind of quadrupole clocking location to actually constrain the detector polarization angle to distinguish B mode and also E mode. And this is what we did. We stacked these maps together. Here it is. We see the quadrupole pattern, and also by bootstrapping, we can reach sub-degree precision with this method. So this is very important for the field to calibrate these instruments. So then moving over to Simons Observatory, this is another thing we're actively working on. Simons Observatory have 3 small aperture telescopes similar to CLASS, and also one large aperture telescope. Right now, the calibration analysis is ongoing. Even before the instrument is deployed, we are first learning from previous experiences, previous experiments. And then we basically, before we have the real data, we simulate raw data considering detector noise, atmospheric noise, and then the calibration analysis is actually underway. Something we are bringing in as new is the drone calibration. Recently, we flew the drone as seen here. This is the plateau of the Atacama Desert. You can see CLASS, ALMA, ACT, Simons Observatory, Simons Array. We flew the drone around here, and all the experiments are looking soon will be joined by Simons Observatory, large aperture telescopes, small aperture telescopes. So, so this is, we will see whether it will work out. It's still an active research area, and if it works out, it will give us a possibility to achieve new accuracy in calibration. So here's the conclusion. Calibration is as important as building the instrument itself, and it has become the bottleneck for CMB experiments. We have demonstrated that we could calibrate the 40 gigahertz telescope with the moon within class in terms of efficiency, pointing, beam, far side lobes, temperature to polarization leakage, detector polarization angle. And we are developing calibration pipeline strategy for Simons Observatory as well, especially the drone calibration strategy. Thank you so much.